Vamos a ver a continuación
Let's see next two examples of practical systems of equations, which they come from mechanics and electricity. Specifically, let's start with the example of the inclined plane. Consider a case of a mechanical system consisting of two inclined planes, a pulley, and then four masses, that are placed together by some ropes or wires. Let's assume that the system slides from left to right. We are also going to make the hypothesis that there is friction, and that the friction between the masses and the planes are different for each of them. Therefore, μ1, μ2, μ3, and μ4, they will represent the coefficients of friction, and m1 to m4, are the masses that we consider. We also see that the two angles are alpha and beta, so that inclination of the two inclined planes do not need to coincide. So, let's see how we solve this problem. First of all, you have to keep in mind that the fundamental basis to all this is the Newton's law, that says that force equals mass by acceleration, that is, if I have a mass, the acceleration that goes to experience that mass, it depends on the strength that is applied in each case. Then, what are we going to do? We are going to isolate each of the masses that appear in this problem, and we're going to replace the elements that act on them by the corresponding forces. When there is a rope, we put a force, which is the one produced by the rope. There will be masses that have only one rope, like m1 and m4, and others that have two. One will be subject to a force and another to two. Then, you must have in mind that the masses have corresponding weights, which are vertical, by the force of attraction of the Earth, which decompose into a tangential component, in the direction of the inclined plane, and a normal component, which is the one that will give us the friction force. So we need to add the friction forces. So, in the schemes up there on the right, you have the four masses, with all the forces to which they are submitted. For example, the mass m1 is subject to force T1, which is the only rope that pulls it. The F1 is the weight component, parallel to the inclined plane, and the N1 is the component of friction, the component which is orthogonal to the inclined plane, and, therefore, the friction force will be the coefficient of friction by the value of that force, which is perpendicular. In the case of the mass m2, we have two ropes, one at the top and another one below. Therefore, there are two forces, one is T2, and another is T1, in the opposite direction, and its weight appears that it is the vertical force, which decomposes in one that is F2, which is parallel to the inclined plane, and N2, which is perpendicular to it. Then, another friction force appears R2, which is its coefficient of friction μ2 times N2, and we can do the same with the other two masses. Then, the values of forces F and R are those that have U down there. They are m times g, of the weight corresponding to that mass, and then, sines or cosines appear, of the angles of the inclined planes, alpha and beta. Those are the formulas that give F and R. Newton's law says that force equals mass times acceleration. Then, for each one of the masses, let's put all the forces that act. In the first mass, we have T1, F1, N1, and R1, with their corresponding signs, and that is equal to the mass, which is m1, times the acceleration a. Look, the accelerations, since the masses are joined all of them, by ropes, they are the same for all masses. The second mass has a total force, which is given by T2 minus T1 minus F2 minus R2, and it is equal to its mass times the acceleration. The same goes for the M3 and M4 masses. These equations can be expressed, in matrix form, setting as unknowns T1, T2, T3, which are the tensions in the ropes, and the acceleration a passing everything else, to the independent terms side, or to the coefficients side. With this, we have a system of 4 equations, with 4 unknowns, which is the one that appears in expression 2. To study the compatibility of the system, what do we do? As the vector of the independent terms must belong to the orthogonal subspace generated by the column vectors of the coefficients, we use the algorithm, and we enter the column vectors, which are -1 1 0 0, in iteration 1, 0 -1 1 0, in the iteration 2, 0 0 -1 1, in the iteration 3, we pivot, and in the fourth iteration we enter the m1 m2 m3 m4, but we do not have to pivot, because if we multiply m1 m2 m3 m4, by the fourth vector, which is the only one with which we can pivot, we get m1, plus m2, plus m3 plus m4, and because the masses are positive, you see that that scalar product is non-zero, so we could pivot. Then, we can pivot with all vectors, that is, the subspace orthogonal to the one generated by the column vectors of the coefficients, would be vector 0, which tells us that the system is always compatible. Then, using the algorithm and the compatibility methods, we have been able to check that this system is always compatible. If the system moves instead of left to right, right to left, we should consider the new equations, with some changes of signs, and this equation would arise that appears there, that can be shown that effectively, it is always compatible, as it was the case in the previous case. Next, I will explain the example of electrical circuits. In this second example I will consider the case of electrical circuits. For simplicity, let's assume that our electric circuits are made only with resistors and batteries. As an example, we have the one in the figure. The poles of the batteries can be connected in series or can be connected in parallel, and they can connect in favor or against, that is to say confronted, and that must be taken into account. Let's see that all the problems of electrical circuits can be solved with two fundamental laws. The first is the law of Ohm, that tells us that when a resistance is connected to a battery, the relationship between voltage and the intensity is that V, which is the voltage, is equal to the resistance R, by the intensity I, that is, V equal to R times I, that's the Ohm's law. There is also another very important law, which is Kirchhoff's law, which establishes that the algebraic sum of the voltages of a closed loop has to be equal to 0. You have to be careful, because some voltages are positive, and other negative, depending of the orientation of the batteries. In this example, we are going to analyze a concrete electrical circuit, which is the one that appears in the figure. There we can see that it consists of 3 cycles or 3 loops, the one on the top, which is the larger one, and then the 2 in the lower part. Let's see what the Kirchhoff's law gives when applied to the upper loop. In this case, we have that there is an intensity I1 circulating through R1, R2, R3, and R4. Therefore, the term of the matrix R1, R2, R3, R4, is multiplying I1, in the column matrix, but also through the R4 resistance, circulates the intensity I2, from the circuit below and, in the opposite direction. That's why the term minus R4, which multiplies I2, and that's all that appears in that loop. Let's go with the loop in the lower left. Over there, it circulates, on the one hand, through the resistance R4, L1 and L2 circulates, and through R5, I2 and I3 circulate, but you have to take into account the signs of each one. Then, considering the signs, we see that I1 circulates through R4, and since it is in the contrary direction, it is minus R4. I2 circulates in the direct sense, by R4 and R5, and then, they appear with a positive sign. However, Intensity I3 circulates in the opposite direction, and that's why R5 has a minus sign. Last, we have the loop on the right, where other intensities also appear as we see next. First, the intensity I1 does not circulate, there is no resistance in this case, then it does not appear anywhere. The intensity I2 is multiplying by resistance R5, but it goes in the contrary direction, so it bears a minus sign. Finally, intensity I3 goes in the direct sense, both for R5 as for R6, and then they appear with positive signs. Analogously, the independent terms that correspond to the voltages, you have to take into account also if they go inside the battery, from plus to minus, in which case they carry minus sign, or if they go in the opposite direction, in which case they carry the plus sign, and there we have the equations. How can we check if this system is compatible? To study the compatibility, we have to see if the vector of independent terms belongs to the subspace generated by the vectors of the coefficients, but the column vectors. For that, we started, for convenience, so it does not get too complicated, with the third column of the matrix, that is, 0, minus R5, R5 plus R6, that we enter there, we calculate the scalar products and we pivot. We enter the second column, which is less R4, R4 plus R5, minus R5, and we pivot and enter the third column, which is the most complicated one, which in this case is the first column. When calculating the scalar product we get the H value, which has that expression, which is a bit complicated, but it could be obtained, and it turns out that all that, because all the R's, the resistances, are positive, and the denominator is also a product of resistances, all that, is a non-zero number, which is greater than 0. Therefore, we can pivot again, and then, because we were able to pivot all the times, it turns out that the orthogonal subspace is the zero vector, and therefore the system is always compatible.